Okay, any questions on Michael? Number 3?
Yeah.
Like the whole thing?
The
Or?
last one.
D.
D. Wait. Yeah, 3D.
Okay, so if you look at, if you look at what's happening in number 3, right? So here's a sack of grain and you're lifting it up. So are you going to do work to lift it up?
Yes.
Right? And what's that? And that work is doing one of two things. It's either creating some form of potential energy or it's creating some form of kinetic energy. So what's it doing?
Kinetic. Wait.
You're lifting it up.
Oh, potential.
Yeah, you're storing potential energy.
Yeah.
So once you get the work that's done, because if your answer to 3A is wrong, everything else is going to be wrong, okay? So your answer to 3A should be around 5,000, okay? So that's what you bring to the dance, okay? That's all. Now, you can change its form. So this is the deal where if nothing else, set up a chart and go, okay, hey, I can have some UG here, I can have some kinetic energy here, I can have the sum. So at any point, once you know what you do to lift it up, that sum, which is about 5,000, that's it. Everything at any point has to add up to 5,000. So when this thing lands here, that's how much energy it has because that's how much work that you put into it. Okay? So on 3D, if that goes well, your velocity should be around 30 meters per second. Okay, that's an ish, but it should be something around 30. Okay? Now, on number 5, basically if you do number 5 right, and it's what we talked about yesterday. So on number 5, here's the idea. Is that you're going to throw this thing down, so you're going to have some potential energy, and you're going to have some initial kinetic energy. So this is going to be your V naught, because this is going to be the initial velocity. And here's what's important. It doesn't make any difference which direction I throw this ball. Throw it up, throw it down, throw it horizontal, throw it on a diagonal. It doesn't make any difference, okay? Because this is a scalar quantity. It does not make any difference in terms of the amount of energy that you give this thing. Now, when it lands, how much potential energy does it have? 0. So at that point, it's all kinetic, which is going to be 1/2 mv squared. So these two values added together here have to add up to what?
Total kinetic energy at the end.
Yeah, this. So if you play your cards right and you cancel out the m's and you multiply by 2, because that's what I would do because I hate fractions. What you should end up with is just that equation. Literally, what you get is that equation.
Oh, yeah.
And when I gave you that equation, I said eventually you will prove where this equation comes from. And that equation comes from the conservation of energy. Okay? That's where that equation comes from. It's the conservation of energy. Okay? We're good. Now, let me explain number 7. Number 7, where I got the idea for that problem, I was in the outback of Australia, and it was out kind of like a state fair.
Where
And, huh?
Where haven't you been? I didn't even know.
Oh, there's a whole, might not been China, Japan,
Been to Canada?
been to Canada. Yeah.
Mankle.
Europe? Yeah.
I've been
Not a lot of Europe, but some.
south.
So anyway, so they were trying to show like what happens if you're not wearing a seatbelt and you're in a collision, because Australians are worse than Americans about wearing seatbelts. Okay, they're this independent lot. Bloody hell! I don't know. Okay, so anyway, so they had this car lifted up, and they dropped. It was pretty cool. This massive crane, and they had the car that just dropped it, came straight down. They crashed on the inside, and wasn't wearing a seatbelt. It was horrific actually. Anyway, so that was the basis of this. So there's a couple of different ways you can work this problem. You can work it from an energy perspective and go, oh, up here it has UG, which is going to be mgh. Oh, when it lands down here, all of that UG is converted into kinetic energy. And you can set UG at the top, that mgh equal to 1/2 mv squared. Now, why didn't I give you the mass of the car? You don't need it, it cancels out. Okay, and if you're really hung up on it, make up a mass. Make the mass 10 kilograms, I don't care. It's gonna cancel out anyway. Anyway, so that's one way you can do it. You could just use that equation, okay? You don't have to do it from an energy perspective. You can just use that equation, okay? On number 8, every answer on number 8 should start with a 1. Talk to me.
Can you help me on 8D?
On what?
8D?
D?
Yeah.
Okay. Here's the deal. What's your answer to 8A?
1.75 times 10 to the 3 joules.
That's how much joules, that's how much work was done, right? So all of that energy, all that work was done was creating kinetic energy, right? So your answer to B is going to be the same thing as your answer to A, right? Now, when it gets to the top, okay, what's happened to all of that kinetic energy?
Condensation.
There's your answer. So your answer to 8D is the same thing as your answer to 8B. Because you can't have more, Logan, you can't have more potential energy at the top than the kinetic energy that you had at the bottom. And since you're at the top, you have no velocity, so it's all stored as potential energy. So that's the easiest question on the entire assignment. Don't make it difficult. Okay? Anything else?
Number 9.
How come for that one, I did other equals MGH, and I got a different value. Not vastly different, but it's different.
What'd you do?
Other equals MGH,
On which one?
8D.
How'd you even do that?
I did 10 kilograms times the gravity, times 9.8, times, and I did 17.5 minus 0.45.
Where'd you get 17.45?
That's the height,
No, it's not.
or 0.45.
0.45 is like the reference. That's why I said we're judging everything from the point that that rocket engine is shut off. Don't include that 0.45 in anything that you're going to do.
Oh, worse.
Do not, if you have used 0.45 meters in anything other than your first answer on 8A. 8A is the only time you're going to use 0.45 meters. Don't use 0.45 meters at any point past that, okay? Because that's where we're shutting off the engines and that's what we're calling the reference point. Mad Max, what'd you say?
Number 9.
Okay. So number 9A starts off with momentum, okay? And your answers to number 9A should be around 300, give or take, okay? Because you have to conserve momentum. So then, once you get the momentum, you're going to find the kinetic energies. Your kinetic energies, and make sure I know which one is which. Just don't write down 2 numbers and expect me to know which one is which. You have Timmy and you have Susie. Make sure I know which one is which. You should see that Susie's kinetic energy is bigger than Timmy's. Okay?
Why is that?
Because it's 1/2 mv squared.
Okay.
Because that velocity is squared, any small changes to that velocity are more important and are mathematically make a bigger difference than the changes to mass. Because that value is squared. Okay? Anything else? Once, twice, so get those added in.
Since it's diabetes and bad.
Give me the recipe for the potato pancakes, dude. Yeah, pass me the diabetes.
Huh?
Pass me the diabetes.
Okay, so the test over, well, here's what we have left. So you got energy, the test over that's looking like it's going to be like a week from today.
Oh, dude, 2 tests in 1 day.
Huh?
2 tests in 1 day.
It's gonna be terrible.
Because that means no homework.
Yeah?
Yeah, but
So
it's
what's the
also
other
gonna
thing?
suck.
Recalc.
Oh, that doesn't count. And then we've got like some random thermodynamic stuff on gas laws and heat and that type of thing. And then there'll be another test on that, and then basically you've got a lab final, or the written final, and then your lab final. So we've got about 4 weeks left, so that's kind of where we're at. Okay, so here's what I like about springs, because especially with you guys, this is going to come like full circle. Because if you remember the very first lab that you all did in this class, is that we said, okay, I gave you a 1/2 kilogram mass, and I said, we're going to take that 1/2 kilogram mass and we're going to suspend it from the string, or the spring, and we're going to measure the elongation. And at the time I said, just accept it, just take 0.5 kilograms, multiply it by 9.8 meters per second squared, and you're going to get the force. And you're going like, okay, whatever, we're doing physics, all right? And it was cool, right? And if I gave you that lab now, y'all would be like, that's it, that's all we have to do. Because now y'all understand, oh, there's gravity, and that's the acceleration due to gravity, things like that. But the cool part about springs is that from an atomic perspective, they're one of the few materials in the world that have like a memory, okay? In the sense that, so you have the steel made out of protons, electrons, and neutrons, the same fundamental particles that make up all of you, okay? But if I take this and hook it on here, and it stretches it, so something on an atomic level has to stretch, okay? The electron cloud, the nucleus, something has to stretch, right? Okay, gets bigger. But if I take it off, then those electrons, protons, and neutrons have a memory, and they go back to that same condition. And no matter how many times I do this, it's always going to go back to that same thing. So it's one of the few particles that have that sense of memory. Because you take water, for example, okay, hey, water's contained in your glass. And you knock over that glass, and that stuff is going to spread out. Well, the water doesn't remember like where it was, and it goes, oh, okay, everybody, let's get back into the glass. Okay, get back, okay? Oh, the water goes, screw you, free at last, okay? It's not getting back in the glass, right? But that's what's cool about springs. Even though the spring is made of protons, electrons, and neutrons, just like water molecules are, water molecules don't have a memory, but the spring does. And so that's the cool thing about it. And if you look at springs, springs actually have a very broad use. And basically, so many mechanical systems involve springs, like tensions on your idler belts in your cars. Even like if you have a mechanical watch, there's springs inside of there. They're on, doors to make them close. There's any number of things where we use these. So that's one of the coolest things we figured out is like, how do you make springs? Okay, all right. Now, if you remember back in the middle of August, way back, and we said, okay, we took a 1/2 kilogram mass and we multiplied 9.8 and we measured it, and let's say it stretches 5 centimeters, okay? So back then, way back then, what did you all graph and why? What did you put on the x-axis? Force or elongation?
Elongation.
Elongation.
Put force.
No, use force.
You put force on the x-axis.
Yeah, that-
Why?
that was right.
Independent, dependent variables.
Yeah.
Oh yeah, what?
Force.
It's what?
It's the independent.
Yeah, force.
Yeah.
Independent. Connect our words together here, okay?
It connects in my brain.
Okay, well, let's articulate that connection for others to hear.
All right. Well, you changed the force. The force is the independent variable.
And that's what's graphed on the
X-axis.
x-axis. So way back when you were like, physics babies, okay? You put force here, and that was measured in newtons, and you put elongation here, okay? And you got this nice sloping line, and we did physics, and you found the slope, and life was good, and wow. Okay, here we go, we're off to the races. So we're gonna do the same thing, but now we've got to switch it up. So when you deal with springs from an energy perspective, and it'll make sense later on why this works. So from an energy perspective, we actually have to flip this script a little bit. So when you're dealing with energy and something known as Hooke's law, and that's what springs tend to follow, you actually have to put the force here, okay, in newtons, and you're going to put the elongation here, which is going to be shown by the letter X, measured in meters. Now here's what's important. This is elongation. It is not the length of the spring, okay? Or if you're compressing it, it's how much the spring is compressed, okay? So here's what's important. It is not the length of the spring. It's how far it's compressed or expanded. So with that said, I'd have 4.9 newtons. Out here, that'd be 0.05 meters, right? Now, is this graph going to go through 0, 0? Felix, is this graph going to go through 0, 0? Really? So if I apply no force to the spring, how far does it stretch? Nowhere. So with that said, will this graph go through 0, 0? Yeah. Okay, graph's going to go through 0, 0. Because with no force, I get no elongation. Now, here's what's important, is that if I take 1 kilogram mass and put that on there, right, I get a much greater elongation. So what that means is that the more force that I apply, the more elongation that I get. So this is what's known as Hooke's law, okay? This is a linear relationship between force and elongation. The more force that you apply, the more it stretches, okay? So here's what's important. This is not a constant force, okay? This is a changing force over a changing distance. So let's look at this. I got force here, I got elongation here, right? So first question, could I find the slope of the line?
Yes.
Yeah.
Yes, Nathan, how can I find the slope of the line?
Oh, so you
Ethan, sorry,
do the change in.
close. I was off by a letter. 2
Change
letters,
in
okay.
whatever, change in that.
Change whatever, change next, right? So I'm going to have 4.9 meters minus 0 divided by 0.05 meters. So, great. Take 4.9 and divide it by 0.05.
You got 18.
4.9 divided by 0.05.
Oh, I missed the 4. I always, when I get stressed out in these situations, 98. I just don't want Mary to. I just don't want Mary to beat me to it. Okay.
It's just
Calculator one.
okay. All right. So what units do I get? Don't make this difficult.
Kilograms.
No, don't make this difficult.
Joules.
Okay. Do I get
Wait,
Newton
never mind, never mind,
meters?
never mind. Oh, I take that back. Sorry.
Or do I get Newton per meter? Big difference. Okay.
Sorry.
This is newtons per meter. If it was Newton meters, it would give you joules, but this is newtons per meter. Now, when you have a graph like this, which you're going to see this a lot, that slope is what we call K. And that K is what's known as the spring constant. And this is going to be different for different springs. So let's say that you had like a much stiffer spring, okay? So this is a fairly lightweight spring. If this was a stiffer spring and I applied 4.9 newtons of force to it, how much elongation would there be? Would there be more or would there be less?
Less.
Be less. So the slope would be
Small. Bigger.
bigger. So the bigger the value of K is, the stiffer the spring, okay? Because what that means is that it takes more and more force per meter to cause that elongation. So the value of your spring constant gives an indication of how stiff that spring is. Okay, so I got this. Here's my spring constant, lowercase k. 98 newtons per meter. So this is a linear relationship. Everybody cool, right? So that means we can write this as y equals mx plus b. Now, Felix, what's my y-intercept?
I'm behind.
Felix, what's my y-intercept?
0.
If anyone should know the
Right.
answer, it's you, right?
0.
0, okay?
Brain caught up there.
Okay, you're good? Caught up now?
Yep.
Okay, all right. I want to leave you behind, man, okay? All right.
Already left.
That train's already left the train. Okay. So what's graphed on the y-axis? 4. So could I write this as f equals my slope, which we said was k, and my elongation is x? Little f equals kx? Okay? Now, so if you look on your equation sheet underneath the force ones, you're going to see that F for the spring equals Kx. So this is where this comes from. So on your equation sheet, you've got F equals Kx. And it says, like SP, to indicate this is the force acting on a spring. Okay? So it's on your equation sheet. All this is y equals mx plus b. It's just a linear function. That's all it is. Don't flip out. Okay? All right. So I got F equals Kx. Now, here's the $1 million question, amongst many other ones. Could I find the area underneath that line?
Yes.
You can.
I can.
Why don't you just multiply?
Now, this looks surprisingly like a what? Oh, that looks surprisingly like a triangle. So, since this thing looks surprisingly like a triangle, Vonda, how do I find the area of a triangle?
1.5 base times height.
Beautiful. Okay? So, Vonda, you're not done yet. You're okay. I got faith in you. At the end of the day, I'm going to multiply a force by a distance. So what do I get when I multiply a force by a distance? Work. Ah, nice. Nice. So the area underneath this line is going to represent the work that's done, right? Because I'm going to take force times distance. Go with this. So, Vonda said it's 1/2 base times height. So I'm going to have 1/2 my base, which is going to be my elongation, which is how far it's going to stretch. And then my height is my force, right? But we're going to do a little bit of voodoo, just a little bit. Up here, we said F equals Kx. So here's my question. Can I take Kx and put that in for force?
Yeah.
Legitimate, because they're equal, right? So I'm going to rewrite this a little bit. And Vonda said that was work, which it is. And then I'm going to have 1/2 x times kx. So if I take k times x, I get,
Kx squared.
now, so I got work equals 1/2
Which is the same thing for kinetic
kx
energy.
squared. Now, here's the $1 million question. When I do this and pull down, what type of energy am I storing?
Potential tension.
Potential energy. So me pulling down on this spring is the same idea as me throwing this weight up in the air, right? So when I store this, I'm storing potential energy. When I let go of this thing, what's going to happen?
Kinetic.
Yeah, right? It's going to go flying up because of the fact that Mother Nature hates potential energy. Okay? Hates it. They've never gotten along and never will get along. So, if you look at this and go, okay, I did work. That's 1/2 kx squared. That's storing potential energy, which we're going to call energy stored in a spring. So down below on your equation sheet, you have two equations that relate to springs. Okay? One says F equals Kx, okay, which is just basically says the more force that you apply, the farther it stretches. So that's on the left side about a third of the way down. And then towards the bottom of that left-hand column, you have another one that says, oh, here's the potential energy in the spring. which is 1/2 kx squared. Okay? So those are the two equations that relate to spring. One relates to energy, one relates to force. Now, but here's what you have to watch. If you look at F equals kx, if I'm just going to get this straight. I have no idea where that is.
Max is getting it.
That's what I figured.
Okay. You're younger than I am, and you had your gallbladder. Okay. So, weird. All right. So when I pull this thing down, I'm doing some work, storing potential energy. So if I double the distance that it stretches, if I double the distance that it stretches, what has to happen to the amount of force that I have to apply?
Doubles.
It doubles. Why?
It's a linear relationship.
It's just strict. Doubling is a linear relationship. So if I want to double the elongation, I have to double the force. Cool with that? Now, but if I double my elongation, what happens to the amount of energy that I store?
It quadruples.
That goes up by a factor of 4. Why?
Squared.
Because it's squared. So doubling the distance doubles the force, but it quadruples the energy that's stored. Okay? Because one's linear and one's a quadratic function. Okay? Good with that? No worries there. Okay. So, and this is just like a linear deal. If I said, okay, hey, if I apply 6 newtons of force, how far is that thing going to stretch? Well, that's simple. You go up here and you go, oh, I got 6 newtons, that's my force. I know my spring constant is 98 newtons per meter, solve for x. Okay? Or if I say, hey, I want to stretch this thing 0.08 meters. Okay? Hey, I want to stretch it a little bit farther. I want to stretch it specifically to 0.08 meters. It'd be the same thing. Come in here, put in 0.08 meters. You know what your spring constant is, calculate the force. But here's what you have to remember. This is what gets screwed up more than anything. This graph, and what you're graphing is elongation. It is not the length of the spring. Okay? It is not the length of the spring. It's how far it stretches. Just keep that in mind. All right, now, things are going to get a little bit more complicated. So let's say I want to take this cart, and y'all did a lab with carts. Remember, you pushed them into the wall and they bounced off, okay? And you had to draw the velocity time graphs. You're all flipping out going, oh my God, it's slowing down really rapidly. Okay, right? So now we're going to look at the same thing, but now we're going to look at it from an energy perspective. So when this cart is just rolling, what type of energy does it have? Kinetic. Okay? Now, we've got a plunger on the end that oddly enough involves a spring.
Potential.
Oh,
Yeah.
oh, like that, right? So, if I give this a push and it hits my hand, what's going to happen to that kinetic energy?
It's going to be stored as potential.
It's going to start to store as potential energy. Now, when the spring is fully compressed, when the cart has stopped, how much kinetic energy do you have?
Zero.
Zero.
Big fat goose egg.
Big, just not a goose egg, but a big fat goose egg.
Yeah.
So let's say it had 10 joules of kinetic energy because it was moving. So Leslie, if I had 10 joules of kinetic energy because it was moving, how many joules of potential energy could I store in the spring? Yeah, because the energy has to be conserved. So by you pushing, if you think about it, and this is where energy is kind of cool. So by me taking a certain amount of kinetic energy and having it hit the wall and stopping it, and I've got 10 joules of kinetic energy, that's going to still store 10 joules of energy in the spring, which would be the same idea as if I threw it up in the air and I gave it 10 joules of, if I gave it 10 joules of kinetic energy, I could store only 10 joules of energy at the top. So me pushing it into a wall and having it stop is the same idea as having it go up the hill. It's the same, all we're doing is storing that energy as a different form. Okay? Cool with this. All right, so let me throw some numbers up on board, and if you want to stand up and take a stretch, this would be the time, because I got to write for a little bit.
This episode of Physics on It brought to you by Coca-Cola.
I'm not even. That's what I did.
Okay? Okay.
You should consider it.
It was for
Wouldn't
camp.
he be a good tutor?
Huh?
Wouldn't he be a good tutor?
Eric?
Eric.
Yeah, he'd
Good
be
what?
fantastic.
Yeah, you can tutor.
Yeah.
A good what?
Tutor.
Tutor. I thought you said suitor.
Well, you know.
Kind of, you know, orange charm, you know? I swear to God, that's what I thought you said. Yes, he would.
Oh, thank you.
Okay. I agree, Tori, he would.
I think he'd grade like you though. It's like he'll start getting mad and write really hard and yell.
Hey, but that's better, because then
Well,
you know,
see,
he knows he cares
and
about
Grape
it.
and I talked about this. So Grape has this cool deal with his, what, iPad?
Oh yeah, and you break the iPad.
And that's my fear, is that, you know, it's like, "Argh!" Okay? You couldn't tell like how hard I was writing.
It has pressure sensitivity. Here's where it can.
No, I got it.
That goes towards the tattoo, right?
It's tattoo money.
No, it's not.
Yeah, it is.
Yes, it is.
No, it's not.
It has pressure
Tattoo
sensitivity.
money.
No, it's not.
Can I go
What are we
talk
at?
shit for a second?
No.
Dang it. I want him to come in here and say that that was donated on behalf of Third Block.
Nope. Nope.
No, you tell. You're
Okay.
gonna have MC, aren't you?
Yeah, but
So-
Super and I are friends, I can just tell him.
So here's the drill. So visualize this. You've got a box, a mouse, a penguin, I don't care what it is. With a mass of 0.3 kilograms, not massive, okay, right? And it's moving at 2.5 meters per second, not all that fast, right? I can, without a gallbladder, I can walk this fast. The block collides with the spring. It has a spring constant of 3,000 newtons per meter, much stiffer than this spring, because this spring constant was about 100, okay? So this is a much stiffer spring. And so it's going to collide, right? So here's your setup if you're a visual kind of person. Here's the box. Here's the spring. It's anchored against the wall. It's going to hit this thing, and then it's going to start to store this energy, okay? Got the idea? So here's what I want to know. And we're going to do some different things with this. But I want to know how much kinetic energy and what is the velocity when the spring is compressed just 0.01 meters. So 0.01 meters is like 1 centimeter, okay? It's like yay far. So we're not going to compress the spring very far. We're only going to compress it 0.01 meters. So here's the big picture, okay? Here's the big picture. This idea is conceptually the same thing as saying, hey, I'm going to throw a ball up in the air, okay? I'm going to throw a ball up in the air 2.5 meters per second. At a certain height, I want to know how much kinetic energy that it still has and how fast it's going. So instead of storing energy going up, I'm going to store horizontal energy in a spring. But conceptually, it's the exact same idea. So in this situation, what are the two types of energy that you're going to have? But what type of potential?
Spring, US.
I'm going to have us, and I'm also going to have KT, right? Now, I'm not going up a hill yet. We'll get to that later, okay? Everything is horizontal. So here's what you want to do, and I beg of you, you have to get into this habit of setting up these charts. So here's your setup. So here was this thing that was moving along. Mass was 0.3 kilograms. Velocity was 2.5 meters per second. Here's the whole key to a problem like this, is that you want to be able to isolate one pure type of energy, whether that's all potential energy stored in the spring, whether it's all potential energy stored because you're on top of a mountain, or it's all kinetic energy because you're moving on a flat surface, okay? At some point, if you can isolate a pure type of energy, that makes these problems really, really simple to work. Because that's going to allow you to isolate that variable that is your energy constant for the problem. So that's one of the key things you got to be able to do, sit here and go, okay, at what point do I have just one type of energy? So this thing is just moving. So what's the only type of energy that this thing has? Kinetic. I don't have any more room to fall. The spring isn't still decompressing or anything like that. Okay? It's all pure energy. That's it. It is all pure kinetic energy. So what you want to do is set up a chart and go, okay, well, let's look at this actually. So I'm going to have some kinetic energy. I'm going to have a spring involved, right? And for now, that's it. And then I'm going to have the sum. So initially, I'm just moving. So if this thing is just moving along, it hasn't hit the spring yet. So I don't have any us, okay? I'm O for us. Got nothing. This is just a big, fat goose egg, in the words of Gray, okay? So I got nothing stored as us. Nothing. It's not there. So here's the deal. Do I have enough information to calculate the kinetic energy of the moving object?
Yes.
Logan, how can I do that?
1/2 v squared.
Yeah. So this is going to be 1/2 mv squared. Okay, no worries there. So this is going to be 1/2. I got a mass of 0.3 kilograms, and it's moving at 2.5 meters per second. That's going to get squared. Don't forget the square of the 2.5. So what do you get?
0.94.
Is that right, Mary?
Yes, it is.
Okay.
0.94.
Thank you,
Good
Mary.
job.
Mary, do you feel like you're kind of a den mother? You know, is that right? Yes, it is. Okay, so
She's got max.
this is it. This is how much energy you got. 0.94. Not a lot. Okay. Okay. You can kind of visualize this. This isn't like a huge amount of energy. Nothing compared to like yesterday when you're trying to get something into the atmosphere of Mars and you're like 10 to the 9th joules. Okay. This is like whatever. So, but here's what's important. Now do I know what my sum is?
Yes.
Yes. Now I know that no matter what, I have 0.94 joules of energy available to me. That's it. That is it. So this is like Shively walking in and he has 94 cents. Okay? He's got 94 cents. That's all. Okay? So he could give 94 people a penny. He could give one person 94 cents. He could split it 54 and 44. It doesn't make any difference. But this is all he has. Okay? There is nothing else. This is all that he has. So I know that no matter what happens later on, everything has to add up to 0.94. This is why if this number is wrong, everything is going to be wrong on a problem like this. So if you ever take the time to look at a number to see if it seems reasonable mathematically, this is the chance, okay? Because if this is wrong, everything's going to be a train wreck, okay? All right, so we got the 0.94 joules. So visualize this. Here's this spring. It's anchored against the wall, okay? And we're going to compress it 1 centimeter. Not very far. We're going to compress it 1 centimeter, okay? So, what can I do with that information? This thing is going to get compressed 0.01 meters, and I've got a spring constant of 3,000 newtons per meter. Hunter, what can I do with these little nuggets of information? I know an X and I know a K.
F equals KX.
I could, but I'm not about the force. You're right, I could do that. But that's not what I want to do. Because I don't want to calculate the force acting on the system. It's not what I want to do.
What is the 0.01 meters?
That's how far it's compressed.
Okay.
That's your X. And you know the spring constant of which is 3,000.
That'll work.
I can do work. I can find work by doing what? Give you a hint, it starts with a 1/2. Find us.
1/2 kx squared.
Beautiful, okay? So I can figure out how much energy is stored in that spring by using 1/2 kx squared. Because I know my x and I know my spring constant, right? So in this case, I'm going to take 1/2. Now, here's why these units have to work out. So this is why this spring constant has to have the units that it does. Because if you notice, I've got newtons per meter, and then I'm multiplying that by meters squared. So I've got newtons over meters times meters squared. One of those cancels out. Then I get newton meters, and newton meters is measured in joules. Okay? So this is why we graph it. This is why we have to put force on the y-axis and elongation on the x-axis. That way I get newtons per meter, and then when I multiply it by distance squared, I get joules. So that's why we kind of have to reverse it from where we started, okay? Because if you have meters per newton, then you end up with like meters cubed per newton, and that isn't what joules is measured. So that's why we have to be consistent on, so we end up with the same unit. All right, so somebody take, now let's think about this. Is this answer going to be bigger or smaller than 0.94? Smaller. Could it be bigger than 0.94?
No.
Why not?
Energy can't be greater.
Yeah, because then we'd have like more energy than what we started with. It would be like Shively is giving away like $1.50, but he only has 94 cents. It was like,
Debt shot.
yeah, okay, no, it's not going to happen. Unless you're the federal government, then they do it all the time. Okay, so with the blessings of Mary, what did somebody get as an answer?
0.15.
0.15.
Yeah.
Mary gives a thumbs up. Do you feel like Caesar, like at the Gladiators? Thumbs up. You know?
That's great.
I love that
Like-
movie.
What was Russell Crowe?
Yes. Oh, I love Gladiator.
Okay. All right.
My dad tried to name me Maximus.
You tried to name
I'm not
it
even kidding.
Why didn't?
Seriously.
I swear to you.
Maximus
That would have
Owens?
fit you.
That would have been cool.
That would have been
Dude,
good.
I don't even know, man.
Maximus
name.
But see, the problem with that is like you had to be a beast. Like,
Yeah.
you can't grow up
Yeah.
Honestly, he named me that, I probably would have been like 4 inches taller and had a beard in like what, 6th grade.
Okay. Just based upon the name.
Yep.
Okay. All right. Genetics or anything else aside, all things would have been equal. You would have been. Okay.
Nature versus nurture.
I understand. Because and of all the scientists that just based upon the name, there's a guy in this is in quantum mechanics, Wolfgang Pauli, who came up with the Pauli exclusion principle. Okay, and his first name was Wolfgang, and it was like if I had a son, I'd name him Wolfgang. Yeah, Wolfgang Burkham. Cool. Yeah.
You know what the strongest man in the world's name right now is? Thor.
Huh?
The strongest man in the world right now, his name's Thor. So just-
Seriously?
Yes.
He was just destined for that.
Yeah, exactly. The name
Okay.
fits it.
Okay, so
Somebody
now,
believes he's gonna kill us.
if this is how much energy is being stored in the spring, think about this. Shively had 94 cents. 15 cents of it he's given away. How much is left?
79.
79 cents. Because this is, of these 94 joules, I've stored 0.15 of it as potential energy in the spring. So now, when we go back to our chart, when do we have 0.94? So when we were just moving along, right, our us, was 0. My kinetic energy was 0.94 joules, and my sum was 0.94. So after we've compressed it, 0.01 meters, we said that us was 0.15.
Yeah.
So that means my kinetic energy is 0.79 joules. So that oddly enough, everything still adds up to 0.94. Now, here's the $1 million question. Olivia, here's how much kinetic energy that I have. How can I figure out the velocity?
You take V equals the square root of 2 times divided by your mass.
Beautiful. So, since kinetic energy was 1/2 mv squared, multiplied by 2, exactly like Olivia said, I divide by the mass, I take the square root of that to get my velocity. Now, before you do the calculations, what does your velocity have to be less than?
Your initial.
Yeah, it has to be less than 2.5, okay? If you get a velocity bigger than 2.5, you've done something wrong, okay? So think your way through the process before you even stare at the oracle. Think your way through and go, wow, does this answer make sense? So somebody take 2 times 0.79 joules and divide that by that mass of 0.3 kilograms. What do you get?
2.29.
2 point what?
29.
Wait, Grape, what did you get? What was your answer gonna be?
I didn't take the square root of it.
You had an answer bigger than 2.5, didn't you?
I did. I 5.26 for camp.
Harry, give him the thumbs down.
There you go.
2.29 Burkamp.
We're good? We're
Yes.
solid with that, great?
She's right.
Okay.
I approve her. I give her my blessing.
Okay, it's too late. You already said the 5, man. There's no way to dig out. Just accept it. Take
She's
the
the one who
beating.
decides that you're your CAD cut.
Okay.
Not the other way around.
So-
give you my blessing.
Seemed like a reasonable answer.
Yeah.
Yeah, it hasn't compressed it very far. We haven't lost a lot of this velocity. Now, here's the last question. What is the maximum, speaking of maximus, what is the maximum compression of the spring? So in other words, when that spring is fully compressed, as far as it can be compressed, how far can we compress it? So here's the deal. When that spring is fully compressed, think about this idea with the cart, okay? When that cart has stopped against the wall like this, how much kinetic energy does it have?
Zero.
0. What's happened to all the energy?
It's stored as potential.
It's gone into the potential energy of the spring, right? So, with that said, go back to your chart. Oh, okay. So this is at maximum compression. So under maximum compression, how much kinetic energy do you have?
0.
0, because it's all stored in the spring. So that's like saying, I'm going to take this cart and I'm going to throw it up in the air. So when that thing is at its highest point, the velocity is 0. That's like fully compressing this spring and making it stop. It's conceptually, it's the exact same idea. So, I got that being 0. Now, how much how much us do I have? 0.94. Why?
Conserve it.
You have to conserve it. It's 0.94. So guess what? What do you think my sum still equals?
0.94.
Oh, funny how that works.
Just like in all 3 cases.
Huh?
Just like in all 3 cases.
Wow! How cool is that? So, now that I know about us, okay, so to speak, now that you know about us, what can you do to find your compression? Shively. Huh.
Pretty good for breaking eye contact.
What? It's breaking eye contact.
Wouldn't you just use us equals 1/2 kx and solve for x?
You're close. But it isn't 1/2 kx.
Oh, kx squared.
Yeah. Equals us, right? Okay? So, you got 1/2 kx squared, solve for x, go to us over k is going to equal x. Square root of that. Cool with that. So in this case, this is a test mathematical calculator equation here. Okay? So I got 2 times us, which is going to be 0.94 joules. And then I'm going to divide that by the K, which is 3,000 newtons per meter. Now, what does your answer have to be bigger than? Yeah, it has to be bigger than 0.01, because at 0.01, you still had some potential, some kinetic energy left over. So if you get an answer that's less than 0.01, you know you've done something wrong. So, let's just go straight to Mary, okay?
Give me a chance, Greg.
All right, I'll give you a chance, Greg.
0.025 or 0.03, you can call it.
No,
Okay.
because 0.03 only has one significant digit.
All right,
And we've been
0.025.
solid, okay?
That's two significant.
So 0.025,
Still has two.
Bigger you should.
Mary?
Good.
Good. So that isn't even that far, okay? That's, you're only talking like 2.5 centimeters, that's about an inch. So you're not compressing the spring very far, even at maximum compression. Now, here's the other thing that you could do with this problem. And we won't, but I'm just going to point out where you could take this to the next step. And say, okay, so here was this cart, it was moving along, hit the spring, right? Eventually the spring became fully compressed, stopped it, boom. Now, as soon as that spring is fully compressed, what's it going to do?
Push back.
It's going to push it back, because Mother Nature doesn't like potential energy. So it's going to push that thing back. Now here's where you could take this to like another level. So you can make it go up a hill, okay? Right? So then you could say, wow, okay, what's the maximum height of the hill? Now, here's what's important. The path that this takes doesn't make any difference as long as it's a frictionless surface. So it could even be like a pendulum swinging up like this. It could be going up a frictionless inclined plane. It could be like a skate park where you're going up a half pipe, okay? As long as there's no friction involved, the path or the mechanism that you take to get there is still going to end up at the same height because it's still going to be all potential energy. So no matter what, you're still going to end up with the same h. So how could you find how high this thing is going to go? Set what equal to what?
Us equal to.
No. You could, but don't. You're going to make it difficult. You're going to set your UG, right? Which is going to be mgh equal to what? Well, or what's the numeric value?
0.94.
Yeah, just set it equal to 0.94 joules. Okay? Yeah, you could set it equal to 1/2 mv squared. Okay? You could set it to 1/2 kx squared. Okay? There's any number of things that you could do, but since you know what that numeric value is, you're just going to solve for h. Okay? Got it? Good? All right, Mad Max. So let me kind of get you started on this. So when you get to question number 4,
I haven't been
okay,
looking at it.
you're going to draw. You're going to take a spring and you're going to have this elongation thing going on. But when you get to question B, it says how much work is done in stretching the spring. Here's what you have to be careful of. You're going to have a graph of force and elongation, and it's going to look something like this. So here's what you're tempted to do. You're tempted to go, oh, work equals force times distance, and you're going to multiply the force, which is the weight of the spring, or the weight of the mass. Multiply that by how far it stretches. Okay, boom, there you go. Okay? But here's the problem. You can only use this when you're pushing something with a constant force across a distance. When you're stretching a spring, you're not applying the same force over that distance, okay? Because of the fact that it's Hooke's law. So when you're applying, like let's say for example, you stopped your car, okay? If you stop your car and you do force distance, that's going to be a horizontal line because you're going to be applying the same force to the car over that distance, okay? So stopping your car is an example of Hooke's law. If you're stopping your car, you can just do FD because it's a rectangle. You're just finding the area of a rectangle. With this one, if you're going to find the area, you have to treat it as a triangle, or you do 1/2 kx squared. But when you have a spring, you cannot do force times distance because the force is changing based upon how far that spring is compressed or stretched, okay? So if it's a spring, you can't do FD. You can still find the area, but the area isn't a rectangle, the area is a triangle, okay? So just keep that in mind. Now, when you get to question number 8, so let me kind of show you the visual of what happens on number 8 when you bungee jump into the Zambezi River Gorge. So back in '98, it took 5 kids that had just graduated, and there we go. Let me see.
What?
How exciting.
Oh, number 1? That should be an easy one to answer.
Giant dam.
Eli, did you say Mays Middle has the best workout room?
In the country?
It's
For middle school,
It's crazy. You showed us some
It's
pictures.
so nice.
Why can't we get a new weight room?
Where's it at?
I don't know. My little sister loves it.
Is it?
Better than those boxes we had to use.
That was horrible.
Little bar.
Yeah, that was so bad.
Isn't that Mays Middle School?
I'm trying to live there in the winter.
So what do you mean, where's that?
No,
Where's
we're
the-
at on the middle school at the
Oh.
Jeez, Nick.
It's Newton's.
Man, the big bar.
Jeez. Have you seen the new middle school? It's like,
They added on to it, haven't they?
it's like not the same at all.
Middle school, scourge on the earth.
Since it's a linear relationship.
Because
Did
K
you
is
imagine
not
this middle school?
I did my student teaching before I the junior high. Swear to God, I'd never set foot in middle school again, ever. Okay, Mad Max.
Oh, we're gone.
Oh, we're still going?
Yeah, I forgot to turn it off.
Okay. All right, so if you ever go to Southern Africa, you need to go see this place called Victoria Falls. And it's this big, massive waterfall, and it's like a mile wide and about 100 yards deep. But then it narrows down into a really narrow gorge. And so what's happening is these kids are getting ready to bungee jump. That's Katie. She's now a nurse here in town. And the other one will be Tim Hawkins, and he teaches out at Barclay College. So, whoa!
I did not know there was a rope attached.
Yeah, there's a rope attached. Yeah.
They're jumping on.
Oh, good.
There she's back.
It's the angle
Wait,
section.
so this is in Africa?
Yes. So this is Tim.
See, it's in here. See, it's in.
So how do you get off of it?
What if you actually?
They hoist you back up.
Outside.
They just cut the rope.
Come on, pull. Get the rope.
Dude, can you imagine? That feeling.
Okay, now.
Oh,
No, we'll get back.
no.
Okay, so here's like bungee out, all right? So bungee cords work because of the fact that when you jump, you're going to fall a certain length before this thing starts to elongate, okay? So you're going to have a certain distance where you're in free fall. So that's what's happening to Tim right now. So Tim has fallen in just like there's nothing attached to it.
It's the real
Okay.
Timmy.
This is the real Timmy. Yes, this is the real Timmy. This is the original Timmy. And so, but as soon as that cord, as soon as he hits the bottom of it, this is going to begin to stretch. Okay, it's going to obey Hooke's law. So as it stretches, what's going to happen to the amount of upward force acting on Tim? It's going to increase. Why? Because F equals Kx. So the farther that he stretches it, guess what? The more upward force there's going to be. Now, what's trying to pull Tim down?
Gravity.
Gravity. So if we're going to stop Tim, what has to happen?
Get rid of gravity.
Yeah, you've got to have an upward force to balance that out. Okay? Because if you don't, Kim keeps falling. Right? Timmy keeps falling. Okay? So here's what's going to happen. So you're here, right? He jumps off. He's in free fall. He hits the end of the cord. That begins to stretch. Then he's gonna start oscillating a little bit. Then to get him back up, they just lift this whole thing back up and he ends up back up here. So if you look at what's happening on the problem that I gave you, I think I tell you that he falls for, what, 12 meters?
Yeah.
Okay? And then he ends up a total distance when he gets done of 31 meters? Okay. So, if he falls for 12 and he ends up 31 meters below, how far did the bungee cord stretch?
9? No, I'm sorry. 19.
19, right? So he's going to stretch 19 meters. So this is your X. This is how far it's going to stretch. Now, here's what we're going to look at. Pretend that the bungee cord isn't involved in this problem at all. Imagine that Tim is standing here and we're going to lift Tim up to a height of 31 meters. If he's down here and I lift him up 31 meters, how can I calculate the energy that's stored in lifting him up 31 meters?
MGH.
MGH, right? So I can do MGH using 31 meters, okay? That's how much energy is in the system, because that's how far he ends up down below. So when this cord gets stretched, what type of energy am I storing when Tim stretches that cord?
Potential.
What kind?
Spring.
Spring constant, right? So this would be the spring energy. So here's the question. This MGH here has to equal the energy stored in stretching the spring, because that's how much energy is in the system. Because this is the easiest way to calculate the amount of pure energy that's in the system, using MGH. So I got MGH here, right? So I'm going to set my MGH equal to the energy that's stored in the spring, which is going to be 1/2 kx squared. Now, here's the $1,000,000 question. The 31 meters is going to be the change in height, because he's going from all the way down to the bottom, and we're going to lift him back up to the top of the railroad bridge. Okay? So this is going to be MGH using 31 meters. Question being is that what do I use for X over here?
19.
Do I use the 12? Do I use the 19? Or do I use the 31? The 19. Why? That's how much stretching is going to occur. So this is going to be 19 meters. So you set your MGH equal to 1/2 kx squared. You know everything here. Use the 31 meters as your height. You know X. The only thing you don't know is K. If all goes well, that value of K should be, if I remember right, I think around 100. Okay? Something like that. So you got to find that spring constant. Now, why don't we like bungee cord with like chains? Why don't we do this with a chain?
Couldn't go.
Because
Yeah, you're going to come to a very, very rapid stop. Okay? So, and that's the balancing act. You don't want them to fall too far, or then they're like going into the river. But you don't want to stop them too abruptly, because then you're going to cause damage. So, we'll finish off Tim's jump.
Timmy!
Where's Mark?
Oh, I didn't.
They did a big cable for Elon.
So, did you ever bungee?
Hold on now.
How many steps did you take?
They make you stare at the horizon, otherwise if you stare down, you tend to lock up and not jump.
3, 2, 1, budget!
And then it turns into a pension. Okay, let me explain what this is.
It was flag.
So, my adopted mother over there was a woman by the name of Mahuka. And in the Ikalanga tradition, like you once you become a mother, then you become Ma and then the name of your oldest child. So like, let's say, Ree, are you the oldest?
No,
Okay, who's your oldest?
Brendan.
Brendan, okay? So, after your mom gave birth to Brendan, she would only be known as like Ma Brendan, So it's always Ma and then the name of the oldest child. Because in the Ikalunga tradition, they place so much importance in becoming a mother because your life fundamentally changes once you become a mom. So it becomes Ma and then the name of your oldest child. So my adopted mother, her oldest boy was the name of Huka. And so I always know her as Ma Huka. And so when I took these 5 kids with me back, she was a principal at a grade school over there. And it was in the rural part of the country. And we were like the first Americans to ever visit the school. And so the kids thought this was just the coolest thing. And so they took rocks and arranged them into a rectangle. Then they took tempera paints and painted the American flag on the rocks so that when we came in, this is the first thing that we saw was an American flag painted on the ground. So they thought, well, this is cool. The Americans have come. So anyway, so that's why there's an American flag that goes on. So anyway, other than that, you're on your own. Be free.
And the ghost through this.
Oh,